today we will continue our discussion on relations. We will see that the relation on a set on a set from a set to itself that we have defined have different particular properties, and we can classify relations based on these properties. Now, before going into all the properties, let us look at let us recall the definition of a relation. By relation from a set A to a set B, we basically mean a subset of the Cartesian product of A by B. So, any subset of A cross B, that is the Cartesian product of A and B, is said to be a relation. Usually when we say that there is an element A belonging to small a, element A belonging to capital A and element B belonging to capital B, they are related if by the relation R if the ordered pair A B belongs to R, and we write very often A R B. Now, we go to particular properties of relations. The first property in this context is called the reflexive property. We say that a relation R on a set A, again to recall that when we say that a relation R is on a set A, that means the relation R is from the set A to the set A, that is R is a subset of the Cartesian product A cross A. Now, if R is a relation on A, we call R a reflexive relation if A comma A belongs to R, that is A is related to R for all A belonging to the set A. Let us try to check one example in this context. Let us see that, let us consider the set Z, the set of integers, and consider the relation A R B if and only if A is less than or equal to B. So, if A is less than or equal to B, where A, B are elements of the set of integers, we will say that A is related to B. Now, we see that given any A belonging to Z, A is less than or equal to A. In other words, A is related to A, and this happens for all A in the set of integers. Therefore, less than or equal to relation is a reflexive relation. Now, let us try to think about a relation which is not reflexive. So, let us take the same set Z, and let us say that for A B belonging to Z, A is related to B if and only if A into B is strictly greater than 0. Please note that here we are specifying that A into B is strictly greater than 0. So, it cannot be 0. Now, let us consider the whether A is related to itself. So, take any A belonging to Z and consider the product of A with itself, that is A square. Now, A square is greater than 0 if and only if A is not equal to 0. So, A is related to A for all A belonging to Z except A not equal to 0, but when A equal to 0, then A 0 is not related to 0, since 0 into 0 equal to 0 is not strictly greater than 0. Therefore, we see that this relation is not reflexive, because there is just one element in the set which is not related to itself. Therefore, we have to be very careful when we are checking for reflexivity of a relation. We have to check for each and every relation, that each and every element, that element should be related to itself. Now, let us check the next property. Now, we say that what happens if a relation is not reflexive. So, if a relation is not reflexive, then well, it is something that it is possible that A is not related to A for at least some A inside the set on which the relation is defined. But if it so happens that A is not related to itself for all A belonging to A, then we say that the relation is irreflexive. That is a second property that we are considering here, that is irreflexive if A not in R, that is A is not in R for all A belonging to A. Now, let us try to find out one example. We can modify the relation that we were looking at. Again we check, yes, we say that we define a relation, let us say R, okay, and R is a relation on Z, the set of integer defined by x related to y if and only if x is strictly less than y, where x comma y belongs to Z. Now, take any x belonging to Z. Of course, x is not strictly less than x. Therefore, this relation is irreflexive. The next in line is the relation, the property is symmetric. We say that a relation is symmetric if A B belonging to R implies B A belongs to R for all A B belonging to A. That is, we consider the elements of A, and if for elements A B belonging to A, and if it so happens that A is related to B, implies always B is related to A, then we say that the relation is symmetric. This is because this means that when we are said there is a symmetry about the relation. So, suppose A related to B, if we switch B and A, the statement will still be true if the relation is symmetric. So, let us look at example of symmetric relations. Now, we have studied congruence modulo m relation. So, x is congruent to y mod m if and only if m divides y minus x. This is the congruence modulo relation where x y belongs to z and m belongs to z plus. Now, we see that if x is congruent to y mod m, then m divides y minus x, which implies m divides x minus y, which in turn implies y is congruent to x mod m. Therefore, congruence modulo m relation is a symmetric relation on the set of integers. We move on to another property which is particularly important, that is called antisymmetric property. Now, a relation is said to be antisymmetric if A related to B and B related to A at the same time will mean A equal to B. Now, let us look at an example of antisymmetric relation. We again consider the set Z and define a relation that is less than or equal to. So, the relation is defined as A less than or equal to B. We know that we will say that A less than or equal to B if B minus A is greater than 0. Now, suppose we have A less than or equal to B and B less than or equal to A, then of course, A is equal to B. Thus, this is a antisymmetric relation. The last property that we will study for the time being is called transitive relation. So, it is like this, that if A is related to B and B is related to C, then A is related to C. And let us look at examples of transitive relations. We can use the relation that we have already studied, that is A less than or equal to B. So, we see that if A is less than or equal to B and B is less than or equal to C, this implies A is less than or equal to C. Thus, it is a transitive relation. We will see other examples of transitive relation soon. Now, let us take some more some examples. Now, we are considering Z to be the set of integers and A, B, C are elements of Z. There is a standard notation to define the equivalence relation, that is this the inverted delta sign. So, A inverted delta, this is the delta, right. So, this delta sign A delta B if and only if A is equal to B. So, this is the equality relation. We can easily see that the equality relation is reflexive, because A is always equal to A for all A belonging to Z, and then it is symmetric, because if A is equal to B, then of course B is equal to A. It is transitive, because if A is equal to B and B is equal to C, then A is equal to C, and in fact it is also antisymmetric, because if A equal to B and B equal to A, of course A is equal if A equal to B and B equal to A, of course this means that A equal to B, but of course we know that it is A equal to B. The next relation is less than or equal to relation, that we have already seen, A less than or equal to B if and only if A is less than or equal to B, and then we have the division A vertical line B if and only if A divides B. We will be reading this symbol as A divides B, and then another relation that we have already seen, that is A is related to B if and only if A B is strictly greater than 0, and also lastly we have also seen the congruent modulo M relation. Now, we come to the set containment relation. Suppose S is a set and P S is the power set of S, and we will say we will define the relation which we denote by this sign if for A B belonging to the power set, A contains B if and only if A is a subset of B. This is a well known relation. This relation is reflexive, antisymmetric and transitive. We will very soon see that this relation makes up an important class of relation called partial order relation. Now, we take up some particular type of relations. The first one that is considered is called equivalence relation. A relation R on a set A is said to be an equivalence relation if and only if the following properties are satisfied: x related to x for all x belonging to A, that is R is reflexive; x is related to y, then y is related to x for all x y belonging to A, that is R is symmetric. If x is related to y and y is related to x, then x is related to z for all x y z belonging to A, that is R is transitive. In other words, if we have a relation which is reflexive, symmetric and transitive, then we call it an equivalence relation. Possibly the most famous equivalence relation is the congruence modulo M relation that we have studied in the previous lecture, and we have considered the example just a while back. So, we are considering the set of integers, and we say that x is congruent to y mod m if y minus x is divisible by m. For example, if we take m equal to 5, then we see that 0 is congruent to 5 mod 5, 6 is congruent to 11 mod 5, minus 7 is congruent to 3 mod 5. Now, let us move on to another relation. This is, we consider the set of real numbers, and we consider the Cartesian product of the set of real numbers. So, we are now in the real plane. So, our points are ordered pairs. We say that an ordered pair A B in R cross R is related by the relation S to an ordered pair C D in R cross R if and only if A square plus B square is equal to C square plus D square. Now, let us start checking what happens. See, we are considering R cross R, and for two elements A B and C D belonging to R cross R, we are defining them to be related by a relation let me so they are defining by the relation S A B S C D if A square plus B square equal to C square plus D square. What does it mean? If we consider the plane R cross R, then we will see that, suppose let us consider the point 1 1 here, then if we draw a circle around the origin O containing 1 1, then all the elements that are in the circle, that are on the circle, has the same distance as that of 1 1. The distance d here is 1 square plus 1 square, that is root 2. So, any element, for any element on the circle, let us say x y, x square plus y square has to be equal to 1 square plus 1 square, that is equal to 2. So, if we consider any other point, let us say A B, all the elements related to A B will lie on the circle around the origin O. Now, let us start checking the properties. We claim that given any A B belonging to R cross R, A square plus B square of course trivially is equal to A square plus B square, which means that A B is S of A B. Therefore, the relation S is reflexive. Next, suppose A comma B and C comma D both belong to R cross R. and A comma B, S, C comma D, that they are related, which implies A square plus B square is equal to C square plus D square. This in turn implies C square plus D square is equal to A square plus B square, which means that C D is related by S to A B. So, the relation S is symmetric. Now, let us consider three elements A B, C D and let us say E F, all elements of R cross R, and A B related to C D and C D related to E F, and this together will mean that A square plus B square is equal to C square plus D square, and C square plus D square is equal to E square plus F square. Combining these two equations, we get A square plus B square equal to E square plus F square. This will mean that A comma B is related to E comma F. Just let us go back. We had here A square plus B square equal to E square plus F square. That means we now have A B is related to E F. This means that the relation S is symmetric. Thus, S is an equivalence relation on R cross R. There is another concept which is intrinsically connected to the idea of equivalence relation, is the concept of equivalence classes. Now, if R is an equivalence relation on a set A, we choose any x belonging to A and then we consider a set which consists of elements of A which are related to x. So, let us try to visualize that we have a relation on a set A and we are picking up one element from that set A, let us call it x, and we are considering all the elements in A which are related to x, and we are building up a set which we will call the equivalence class corresponding to x. Now, in this way we can keep on building equivalence classes of each and every element of A. Then we start questioning that what is the relationship between different equivalence classes, and then we come to a to an observation that if we pick up two elements from a set A, then the corresponding equivalence classes are either equal or they are disjoint. Now, this needs a proof. So, we will check how to prove this fact. So, let us recall X is the equivalence class corresponding to X. So, it consists of all y belonging to A on which X is defined such that y related to X. Now, suppose we consider two elements, let us say small a and small b belonging to A, and build their equivalence classes, which is square bracket A and square bracket B. Now, let us suppose that they have a non-empty intersection, that is to say that the intersection of the equivalence class corresponding to A and the equivalence class corresponding to B is not empty. Therefore, there exists a C belonging to A such that C belongs to A intersection B. Now, this in turn means that C is related to A and C is related to B. Now, this implies that A is related to C and C is related to B, since R being an equivalence relation is symmetric. Therefore, I can switch A and C, they are symmetric. C related to A means A related to C. And now, we will use the transitivity of R, because R after all is an equivalence relation, and write that this fact implies A related to B. But if A is related to B, this will imply that A belongs to the equivalence class of B. So, we see that if the equivalence class corresponding to A and the class corresponding to B have a non-empty intersection, then A is an element of the equivalence class of B, but then let us consider any element in the equivalence class of A. Suppose X is an element in the equivalence class of A, which implies that X is related to A, and since we already know that A is related to B and we also know that R being an equivalence relation is transitive, we use the transitive property over here when we write X is related to B, and X is related to B means X is inside the congruence the equivalence class of B, and therefore, this whole thing together implies that the class corresponding to A is contained in the class corresponding to B. Let us call it 1. Now, we could just change the symbols A and B, and then everything else will hold true, and in exactly the similar way we can prove that class corresponding to B will be contained in class corresponding to A, and combining 1 and 2 we have A equal to B. Thus, we see that if A and B, the class corresponding to A and B has non-empty intersection, then they are equal. So, we come to our conclusion that these equivalence classes are either equal or disjoint. Fact that we prove is that the set of equivalence classes corresponding to an equivalence relation R on a set A partitions a set. For that, we have to first recall what we mean by partition. A partition on a set is a set of subsets of that set which are mutually disjoint and which covers the whole set. That is, for example, if we consider, let us look at the. So, let us consider a set A and P consisting of, let us say, some subsets of A, where this I varies over some indexing set I. We will say, that P is a partition of A if and only if di intersection dj is empty for ij belonging to I not equal to j, and union of di when I varies over I gives us the whole set A. So, suppose R is an equivalence relation on A consider the equivalence classes. So, consider all the disjoint equivalence classes. So, suppose we consider this set, and we are only considering, since it is a set, only the no element repeat. So, we are, this is a set of subsets which are distinct, and we know that distinct equivalence classes are disjoint. We claim that this gives us a partition, because if we have any, if we take any y belonging to A, then y is related to y, which implies that y is in the equivalence class of y itself. Therefore, for some therefore, this set y must appear in this set. So, this shows that if I consider the union of all the equivalence classes, where x varies over all the disjoint equivalence classes, then I will get the whole set A. Further, if we have already proved that if we take any two equivalence classes, either they are same, in which case this x equivalence class corresponding to x and equivalent class corresponding to y will give us only one entry over here, otherwise they are disjoint. So, they will contribute to different entries, and therefore, if we take all the disjoint equivalence classes, we will get a partition. On the other hand, if we are given a partition on a set A, then it naturally gives us an equivalence relation. Let us look at the partition that we have already discussed. We can define an equivalence relation in this way, that suppose we consider x comma y belonging to A, we may say that x related to y if and only if x comma y belonging to d I. Now, we see that x comma x belongs to d I, because of course, x is a single element. So, this is trivially true. So, R is reflexive. We again see that if x and y belongs to d I, then both things, this will imply both things, that x are y and y are x. Therefore, x related to y means this, which in turn of course means this. Therefore, we know that it is symmetric, and further at the end, if x related to y and y related to z, this implies x and y belongs to d I for some I, and y and z belongs to d j for some j, but that means that, let us see aside, that means that y belongs to d I intersection d j. We know that d I intersection d j is phi if I not equal to j, which implies that I equal to j. So, we can say that this implies that x comma y comma z belongs to d I, which means that x is related to z. Therefore, we have transitivity over here. At this point, I will again emphasize that given any x, we will have x belonging to some d I, because union I varying over capital I d I is the whole set A. Therefore, this happens. This is the property of partition that we are using. Thus, we have given a proof of the fact that if we have a set and an equivalence relation on a set, it will generate a partition on the set, and if we have a partition, then that it will generate an equivalence relation. Now, let us look at some examples of equivalence classes. Now, we go back to the example that we saw some time back, which is here. Here we take m equal to 5 and we have congruence modulo 5 relation, and we come over here. Now, corresponding to congruent modulo 5, if we consider 0, let us see the equivalence class generated by 0. So, we have got 0, 5 minus 5, 10 minus 10, 15 minus 15, 20 minus 20, and so on. Now, if we want to find out the congruence class equivalence class related to 1, then we see that it is 1, then so instead of 0 it is 1, instead of 5 it is 6, instead of 10 it is 11, and so on. So, this whole equivalence class that we have got corresponding to 0, we have to shift by 1 and we get this one, shift by 2 we get this one, shift by 3 we get this one, and 4. And now, we note that if we shift this by another 1, so if we add 1 to all the elements, we will go back to the congruence class corresponding to congruence or equivalence class corresponding to 0. So, these are the equivalence classes corresponding to the congruence modulo 5 relation. These are also sometimes called congruence classes. Now, we look at the other relation that we considered. So, the equivalence classes here are concentric circles around the origin. So, we will have infinite number of concentric circles around origin, which are the equivalence classes corresponding to the equivalence relation S, which is to recall that A B comma C D are related by S if A B S square plus B square equal to C square plus D square. So, this is the end of this lecture. So, thank you.